Yeah, good morning everyone. Welcome to the lecture on electrical circuit analysis. So, today our lecture is on Norton's theorem. Today is our lecture on Norton's theorem. So, last class we have studied about the Thevenin's theorem. Now, we are going to study in this today's lecture Norton's theorem. So, what are the learning objectives? That is, today lecture objective is to state the Norton's theorem, and the second learning objective is to apply the Norton's theorem for a solving a network. Okay. So, let us see. So, what is the statement of this Norton's theorem? So, Norton's theorem states that any linear two terminal circuit can be replaced by an equivalent circuit consisting of a current source IN in parallel with the resistor Rn, where IN is the Norton equivalent current, that is called short circuit current, and the Rn is the Norton equivalent resistance or the equivalent resistance at the terminals when the independent sources are turned off. That means any network with any linear network with two terminals circuit can be converted into a single source consisting of a resistance in parallel with the current, that is a Norton equivalent circuit. That means the Norton equivalent circuit consisting of only one source, one current source, that is called Norton's current or short circuit current in parallel with the Norton resistance or equivalent resistance at the terminals. So, if it is AC circuit, then the instead of Rn, that is we can take the Zn, that is the Norton impedance. That means the equivalent impedance at the terminals. Okay. So, how to find out the Norton current and Norton resistance? Now, see, this is a linear two terminal circuit. Okay. So, now this is the two terminals here, A and B are two terminals. So, I want to find out the short circuit current, that is ISC. ISC means short circuit current, which is equal to the Norton current IN. Now, here the Thevenin's resistance and Norton resistance are equal. That means, how you have calculated the Thevenin resistance. So, same process is applicable for to calculate the Norton's resistance. Therefore, here Rn is equal to the R Thevenin's. Now, how to find out the short circuit current from A to B? So, this IN must be equal to this ISC, that is short circuit current. So, that is equal to the P Thevenin's by R Thevenin. That means, we can find the Thevenin's voltage across the same terminals AB and find the Thevenin's resistance R Thevenin's across the terminals AB. Then you take the ratio of V Thevenin's by R Thevenin's, which will give you the short circuit current, that is equal to the Norton's current. Okay. So, to understand this, let us solve one problems on this Norton equivalent circuit. Okay. Now, see, Thevenin's or Norton equivalent circuit, see the open circuit voltage VOC across the terminals AB is V Thevenin's. So, we already solved the Thevenin's problems on Thevenin's theorem. So, V Thevenin's is equal to VOC. The short circuit current ISC, how can we find? So, ISC at terminals AB is IN is equal to ISC. So, the Thevenin equivalent or input resistance R input, okay, R in at terminals AB when all independent sources are turned off. So, R Thevenin is equal to V Thevenin by R Thevenin, that is R Norton's. Sorry, here you can say ISC, V Thevenin by ISC will give you the R Thevenin, that is equal to R Norton's. Okay. So, example 1. So, let us solve the circuit so to understand this Norton theorem. Okay. So, find the Norton equivalent circuit of the given network. Okay. Now, see how you have to draw the equivalent circuit, equivalent Norton circuit for this given network. Okay. So, how to draw the equivalent circuit, how to find out the Norton's current and Norton equivalent resistance, let us see to understand this theorem. Okay. First, let us find the Norton equivalent resistance, that is to find R Norton's. So, what we are doing? So, we have to replace this all independent sources. So, how many independent sources are there in this network? So, two independent sources are there. One is a 2 amperes current source and the 12 volts voltage source. So, these two are independent sources. So, to find out the equivalent resistance, so we have to replace this, we have to kill this independent sources. So, current source is replaced by open circuit and the voltage source is replaced by short circuit. Now, see here 2 ampere current sources get open circuited. and the resistance that is the voltage source is short circuited. Okay. Now, we have to find out the equivalent resistance, that is R Nortons from the terminals Rn, okay, across the same terminals AB. Now, tell me how these combination, how these resistors are connected. So, we are coming from this right side, okay, coming from the right side. So, we should go from the left side. That means, this 4 ohm resistor and this 8 ohm resistor and the again upper 8 ohm resistor, these 3 are connected in series, and this combination is connected in parallel with the 5 ohm resistor. Therefore, Rn is equal to the 5 ohm in parallel with the 8 plus 4 plus 8, because when two resistors, when n number of resistors are connected in series, the equivalent resistance is R1 plus R2 plus Rn and so on Rn. Therefore, 5 is in parallel with 8 plus 4 plus 8. So, that is equal to 5 in parallel with 8 plus 8 is 16 plus 4 is 20. So, 5 parallel with 20. When two resistors are connected in parallel, so the equivalent resistance is R1 R2 by R1 plus R2. Therefore, 20 into 5 by 20 plus 5. So, 25 is 100 by 25. So, to 25 1 is 25 4 is, so 4 ohm resistance. That means, this entire circuit or network can be converted into only one single circuit, single network that consisting of only one current source, that is I Nortons, and in parallel with resistance, that is R Nortons. Now, we have calculated the R Nortons. The next step is we have to calculate the I Nortons, that is the Nortons current, short circuit current we have to find out. So, what is the short circuit current flowing when the two terminals A B get short circuited? See, to find out this, what we are doing is the same network. So, we are making the short circuit, we are making the short circuit across the same terminals A B. Now, to find out the short circuit current ISC equal to IN, so I am using the mesh analysis principle. So, whatever the technique you want to use, you can use it. If you want to use node analysis, you can use it, mesh analysis, you can use it, whichever is convenient for you. Here I am using the mesh analysis. So, let us take this consisting of two meshes. See how many meshes this network consisting of? See, it seems 3 meshes, mesh 1 and mesh 2 and mesh 3. But see here, once this AB is short circuited means, what is the resistance of this AB? So, the short circuit resistance is 0. So, 0 is in parallel with 5 ohm resistance. So, 0 into 5 by 0 plus 5, that is 0. Therefore, this 5 ohm resistor is redundant. We should not consider this 5 ohm resistor because it is short circuited. The current always offer the low resistance path. So, a high amount of current will flow through the short circuit instead of flowing through this 5 ohm resistance. So, therefore, I am considering this only mesh 1. Therefore, here this network consisting of two meshes, one is I1, so mesh 1 and mesh 2 combination. So, first let us apply the mesh analysis. What is I1? First I1 is equal to 2 amperes. Okay. Now, apply the mesh analysis in this second mesh. Okay, KVL, apply the Kirchhoff voltage law in the second mesh. So, this 8 ohms, this 4 ohms and this 8 ohms, these 3 are in series. Same mesh, because 8 plus 8 is 16 plus 4 20. So, 20 into I2 minus, see, this 4 ohm resistor is connected between the two meshes, mesh 1 and mesh 2. Therefore, I2 is entering means I1 is leaving. Therefore, 20 I2 minus 4 I1. So, minus 12 volts. See how much voltage source here? Minus 12 is equal to 0. Algebraic sum of the voltages around any closed path is equal to 0. Therefore, from this, if we solve this equation 1, that is I1 is equal to 2 amperes, substitute this I1 is equal to 2 amperes in this equation. So, 20 into I2 minus 4 into 2, 4 2 is 8. So, minus 8 minus 12 is minus 20. Now, minus 20 is sent to the RHS side, therefore, you will get 20 I2 is equal to 20, therefore, I2 is equal to 20 by 20 is 1 ampere. What is this I2? This I2 here is ISC, short circuit current. So, this short circuit current is nothing but our Norton current IN. So, therefore, our Norton current is 1 ampere. Therefore, what is this is the circuit. Now, this is the given network. Okay. So, this given network we are converting into, so only one network. So, this is what? Okay. Now, see, this is what I told you the given network can be converted into the equivalent network which consisting of only one current source in parallel with the resistance. That current we are calling as a Norton's current, that is short circuit current across the same terminals, and that resistance we are calling as a Norton resistance across the equivalent resistance seen from the terminals AB. See, What is the Norton current? 1 ampere we got, and Norton resistance is 4 ohms. So, this is the equivalent network, Norton equivalent circuit for the given network across the same terminals A B, across the same terminals A and B. Now, see, this is the one step, one method to approach. Now, we can also find the Norton's current by using the Thevenin's theorem. Okay. Now, let us see this. See, Act 2, the alternative method for this I Nortons. So, we find out the I Nortons V Thevenins by R Thevenins. Now, see, from this network, see, R Thevenins is equal to R Nortons. Resistance is same, Norton resistance and Thevenin resistance are same. Therefore, you no need to calculate again the R Thevenins. So, R Thevenins we have calculated, that is the 4 ohms we got. Now, let us find out the V Thevenins. So, V Thevenins is equal to open circuit voltage across the terminals A B. Now, we have to find out what is the actual voltage across these terminals A and B. Now, to apply this, I am using a mesh analysis here. So, first let us see mesh 1 and mesh 2. Of course, these two meshes, let us take the current in the mesh 1 is I3 and current, because already we have taken the I1 and I2. Therefore, I am taking here I3 and I4. Now, apply the mesh analysis, that is KVL in the mesh 1 and mesh 2. So, of course, we know that I3 from this mesh simply from the network. So, I3 is equal to 2 amperes, directly current is given. Now next apply the KVL in the mesh 2. So, again this 8 plus 8 is 16 plus 4 20. So, 20 I4 minus. So, current I3 I4 is entering and I3 is living in this 4 ohm resistor. So, because mutual element, this 4 ohm resistor is connected between the two meshes. So, 25 I4 minus 4 I3. See, 8 plus 8 16 plus 4 20 plus 5 25. 25 I4 minus 4 I3 minus 12 is equal to 0. Now, you substitute this I3 is equal to 2 amperes in this 20 that is in this equation. Therefore, 25 I4 minus 4 into 2 8. So, how much? Minus 8 minus 12 minus 20. So, 25 I4 is equal to 20. Therefore, I5 is equal to 20 by 25, that is 0.8 amperes. 0.8 amperes. Now, once you find the current flowing through this 5 ohm resistor, that is I4. So, what is the voltage across this 5 ohm resistor? So, voltage across any resistor is equal to, according to the Ohm's law, V is equal to I into R. So, I is 4 into R is 5. So, 4 into I4 into 5. I4 is already 0.8 into 5 is 8 5 is 40. So, 4.0, that is 4 volts. So, how much voltage we got? Thevenin's voltage, that is open circuit voltage across the terminals. So, 4 volts. Then it is easy to find the Norton's current. So, IN is equal to V Thevenins by R Thevenins, that is 4 volts V Thevenins, 4 ohms R Thevenins. So, 4 by 4 is 1 ampere. So, this is the alternative method to solve the network to find the Norton's current and Norton resistance. To find the Norton resistance, what we have discussed that to find the R Thevenins, same, there is no doubt in that. So, to find the R Thevenins and R Nortons, both are same process. So, next let us see the one more example problem. Using Norton's theorem, find R Nortons and IN, that is Norton resistance and Norton current for the given network across the terminals A and B. Now, let us find the I Nortons, and now that means we have to convert this network into the single network which consisting of only one source, that is called I Nortons current source, in parallel with the resistance, that is R Nortons. This entire network can be converted. Now, let us solve this. See here. So, to solve that, so let me take this. So, first to find R Nortons. So, how to find out the R Nortons? So, you have to kill the active sources. See here. What is the independent source here? So, 10 volts voltage source, and this is the only source. So, you have to make it short circuit. 10 volt voltage source short circuited, because see here. So, short circuited here. This is what short circuited. Now, 4 ohms, the current flowing through 4 ohm is Ix, 2 Ix. Now, how to find out this? So, I already told you. So, to whenever there is a dependent sources present in the network, to solve the equivalent resistance, we have to apply either 1 volt voltage source or 1 ampere current source. So, here I am taking the 1 volt voltage source, we are applying 1 volt. So, apply the 1 volt here, 1 volt here. Now, we have to think about that 1 volt. Now, apply the 1 volt. Now, see here 4 ohm resistor is short circuited, because 4 4 ohm is in parallel with the 0, because when short circuited 4 ohm is short circuited with 0. So, 4 into 0 by 4 plus 0, that is 0. So, therefore, 5 ohm resistor in parallel with V naught and in parallel with 2 Ix. So, all are in parallel. Hence, what is Ix? So, Ix is equal to V naught by 5. Ix is equal to V naught by 5. So, therefore, what is the V naught? The V naught is 1 we have taken. So, 1 by 5 is 0.2 amperes. Therefore, from this what is Rn? See, when we apply the 1 volt voltage source, you have to find out the R Nortons is equal to, that is R equivalent resistance Rn is equal to that V naught, that is 1 volt by find the current I naught. So, V naught by I naught. So, V naught we got 1, we applied 1 volt, by I naught we got 1 ampere, that is 0.2 amperes. So, 1 by 0.2 is 5 ohms. That means, so the R Nortons is how much? 5 ohms. Next, to find out the I Nortons, how to find out the I Nortons? See here, you have to find out the short circuit current. See, across the same terminals AB, you have short circuited. AB is short circuited, that is ISC is equal to IN. ISC is equal to IN across the this one. Now, what is this Ix? So, this Ix is equal to, see, 10 by, because the voltage is 10 volts, so 10 by 4. 10 by 4 is how much? 2.5 amperes. Now, therefore, ISC is equal to, now apply the Kirchhoff current law at this node, So, 2Ix plus Ix, okay, 2Ix plus Ix, so that is what? That is equal to 10. So, currents, what is the currents coming here? 2Ix and Ix are coming, but Is is leaving. Therefore, Is is equal to Ix plus 2Ix is equal to, what is Ix? Already we got 10 amperes. So, 10 by 5 plus 2 into 2.5. 2 into what is Ix? 2.5. So, 2.5, that means you get the 7 amperes. You will get the 7 amperes. Okay, 7 amperes. So, therefore, IN is equal to 7 amperes. IN is equal to 7 amperes. So, therefore, this entire network, see, this is the given network. So, this entire network can be converted into, the only one equivalent circuit which consisting of 7 amperes current source and in parallel with how much? 5 ohm resistance. Okay. So, this is the way to solve the Nortons, to find out the Norton equivalent circuit for the any given network. Okay. So, thank you for the listening class. We will join in the next class.